Okay, let's get started. So, who has a question from last time? Anyone have any questions? None? Okay. So, you'll get your quiz at the end of the lecture today. So, what did we talk about last time? Why the sky's blue? Yeah, the input-output machine. So one of the examples we had was this one. So this is just the machine that we looked at last time. I'm not sure if the names of the states are right, but it's close to this. So was anyone able to make a smaller version of the same machine? So how many states did you end up getting? Just 2 states. Yep. And so what's a way that we could phrase the set of strings that this accepts? Says Yasan. What's an English way we could describe them? So what strings does this thing accept? Of odd length, yep. Does it accept any other ones? No. In fact, we can even see that because in Q0, we have the strings of 0 length. And then if we take a transition, then we will be at an odd length, which means we must be in one of the accept states. And if we take another transition, we will be in the Q0, Q3, one of those 2 states. So it's kind of, the parity is switching between Q1, Q2 and Q0, Q3. So, okay, great. So this is all binary strings of odd length. Okay, so that's the machine we talked about a little bit last time. So, great. Well, if I was to present this to a computer, how would you write this machine to a computer? Like, if I wanted to have my computer figure out whether some string is accepted by this machine, how would you do it? If I had to write that machine into a computer somehow, how would you do it? A linked list is an example. Yeah.
You could set a variable, a boolean variable, and just give on and off.
Yeah, that could be true. But I want to actually encode the states into the machine somehow. Well, here's the thing. Could this machine take 2 as an input, for example? Is that possible? Why is it not possible?
Because we can have 2 computations.
There's no 2 written there, but what if I was lazy and I just forgot to put a 2 there? Could 2 be specified as a possible input character? Could it be possible, is what I'm saying. Yeah. So what I think would be better is instead of just saying, okay, let's look at this picture and try to understand what's happening by starting at the start state Q0 and then just reading characters and just seeing where you end up, maybe we should be a little bit more formal about this because we're just looking at a picture and we can look at pictures all day long. But we want to make this a formal idea so that if we look at a picture like this, there could be multiple ways of viewing it. It could be that some transitions are left out, and maybe there are other states that we forgot to put in. We want to make this formal so that there's no ambiguity as to whether or not of what we're actually talking about here. So that's what we're going to do now. So these machines have a really nice name. So they are called deterministic finite automaton. I have no idea how to pronounce that right. And we're going to, from now on, refer to that as DFA. So whenever you see the acronym DFA, then that's referring to this definition. So this is a definition. So let's see. Well, if I want to formally specify what this machine is, what are the things that we need? Well, we need what the states are of the machine, of course. I'm going to write all of this down in a second. So we need states for sure. What else do we need to specify? If we want a complete specification of what this machine structurally is. Well, states, what else do we need?
The entry point.
The entry point, yep, the start state. What else do we need? I think we need to know which of the states have the double circle. Are there except states? So we need that too. What else do we need? Yeah.
The connecting arrows.
The connecting arrows in two respects. One is where the arrows go and what are on the arrows for sure, but also what are the allowed characters on the labels themselves. Because we had a machine last time where we just had 0 only, but this machine has zeros and ones on the transition labels. So we need that too. And in fact, that completely specifies what the machine is. So a DFA then is something called a 5-tuple. So the way that we're going to be specifying these objects is with a tuple. Anyone remember Python tuples? Same idea here. Yeah, same idea. So here, I'm going to provide you 5 things. Capital Q, sigma, delta, Q0, and F. And I'll say what each of these means. So if I give you this 5-tuple and I provide all 5 parts to you, then I'm specifying to you a DFA formally. We could reproduce the picture if we wanted to, but this is a formal way of specifying what the machine is. So what are these 5 parts? So where Q is a finite set of states. So the states of a DFA are specified in a set because there's no repeat states. And we might as well just put them in a set anyway. Sigma is a finite set which we're going to call the input alphabet. And there's actually a really good reason why we're restricting ourselves to a finite number of states versus an infinite number of states, because it changes the model of computation. So we're just going to stick with a finite set of states, finite input alphabet. I don't allow you to have infinitely many input characters. You can only have a fixed number of them. I'm going to skip over delta for now. Well, let's see. Q0, what was Q0 in our machines that we've been talking about? What was it? Yeah.
State.
It's a state, but what special property does it have? It's the entry point. So we're going to have Q0. Well, it has to be a state, as was just mentioned. So Q0 has to be in the set of states, because it's a state, of course. So Q0 is an element of the state set Q. and then we're going to call that is the start state. So, and another thing that's kind of not really that important, but you'll see this several times. The start state doesn't have to be called Q0. And in fact, the state names don't have to be Q0, Q1, Q2, Q3. You can name them other states like New York, Arizona, Nebraska, other state names, right? So it's just that Q0, Q1, Q2 is a convention. It doesn't have to be that way. Okay, well, let's see. What do you think F stands for? Press F in the chat. What do you think F stands for?
Is it perhaps the function or the computation?
That's actually a really good guess, and I never thought of it that way, but it's actually not, sadly. I wish it was the other way around, but it's not. So F actually represents the double-circled states, the except states. Well, let's see. Let's think about this. Well, what do you think F is structurally? Is it like a number? Is it a set? Or what is it? You jumped the gun. So it's a set. It's a set of states because Q1 and Q2, that's a collection of states and there's no repeats. Well, could I have, for example, all of the states not having any double circles? They're all single circled ones. No except states. Could that be possible? Yeah, it would be a pretty dumb machine, but it's valid. It's possible. Could I have every single state being an except state? Yeah, it would accept every string at that point, but it's possible. So what we're going to allow ourselves is that F is just some subset of Q. So I'm going to specify to you some subset of the states. And I'm going to call this the set of final states. You can think of that as accept states or final states. I'm probably just going to use final states from now on because it's F. Okay, so now the one that's most tricky, the one that is the hardest part among all the definitions we're going to encounter in the class, which is the delta, which we're going to call the transition function. So delta is a function, which we're going to talk about what it is in a second, is the transition function. But then I have to say what the transition function actually does. Well, let's see. Let's look back at our picture. So let's just say that we're in Q1 right now, and I see a 0. What's the next state? It's Q0. So something that's kind of crucial here. So what does the first letter of DFA represent? Deterministic. So if I said Q1 on input 0, could there be multiple states? It's deterministic. It'll always do the exact same thing every time. So if I say Q1 on input 0, how many possible states are there? Exactly one. There's always one defined. So it's not like if I get to Q1 and I have a 0, I'm stuck or something. I will always have a transition to take. But also, when we took that transition from Q1 on input 0, what are the only pieces of information that you need to know in order to successfully take that transition? Well, you need to know where you started from and what else. In order to execute this transition in particular, what information do I need to know?
The next input.
The input character, right. So I need to know where I'm starting from, what the character is I'm going to read, and where am I going. So I need to know what the state is that I started in, and what input character that is. Well, if I know what the state is and what the input character is, does that tell you exactly what state to go to? Yeah, there's exactly one possible output. So the transition function then is of this form. We're going to take some state cross some input character. So this is an ordered tuple right now, where you take the state and the input symbol that you're considering, and the output of that function is the next state that you're going to. So it's just a state. So I'm going to put in a different color what these mean. So the Q on the left side is the, I'm going to call it the origin state. The sigma here is the input character. And Q on the right side is the destination state. So we have origin state, input character, destination state. But it turns out that we need something else along with this. So I mentioned that for every single state and input character combo, there's always a state to go to because it's a deterministic machine. So what we actually need is that no matter what state and symbol that you pick, there is something defined. So what we need here, additionally, delta is, I'm not sure if you've learned this term yet, but you'll learn it now, is a total function. And what in the world does that mean? That means that for every state Q and some symbol S in sigma, delta of Q with that symbol is defined. That's all that means. Note, I did not say injective, surjective, or bijective or anything. So all that we need is that every state and every symbol are defined, which means that no matter which one you pick, you can always go to another state. Does this say that every state can be reached? No, because I could just have a state, I can remove some of the transitions and point them somewhere else if I wanted to. So it doesn't have to be that every state is reachable, which would change the meaning of delta here. All we're saying is that every input combo is defined. There always is a transition that you can take. Any questions on that or confusion? Okay, cool. So I want to define some other things. So here's another definition. Actually, there's going to be quite a few definitions today. So it's kind of a boring day. So let's let sigma be an alphabet. I'm actually going to leave off finite here because for reasons we'll see later. It doesn't actually matter for our purposes right now. We're going to say sigma star is the set of all finite length sequences over sigma. Who's confused on what in the world that means? Okay, good. So if you weren't confused, I would be even more surprised. So what does this mean? This says, actually, let's just do an example. So let's just look at the set 0, 1. So this is just going to be an example. So sigma is 0, 1. So that's my alphabet right now. Then sigma star is the set of all finite length sequences. Well, this means that you pick a number that you want, like 0, 1, 2, 3, etc. Then you pick a string, which is just taking elements out of sigma and repeating them for that length. So let's pick 0. So if I was to task you with picking 0 things out of sigma, what do you get? Empty. We're making a string of characters, so it'd be empty string. Good. So here, one element is going to be epsilon, and what epsilon is the empty string. So that is the result of picking 0 things out of our set. Okay, now what are all the possible ways we could pick one thing and one thing only from our set? No, I'm asking what are they? 0 and 1. Yep. So 0 and 1. Now let's think about the ways we can pick 2 things from our set sigma. What are the ways we can pick 2 things?
0, 1, and 0.
Yep, and they could be the same too.
And then 0, 0.
Yeah. So 0, 0's in there, 0, 1's in there, 1, 0's in there, 1, 1's in there. And then we can start picking strings of length 3 from there. So, So they don't have to be ordered like this, but 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. So can you give me an English description of what sigma star is in this case? Just an informal description. What does it have in there? Well, every string in there has 0's and 1's in it.
Is it every possible binary sequence?
Binary string, yeah. It's every binary string. Cool. So, So this is every binary string. Yeah, so all you have to do is pick something 0 times, which is just the empty string. So actually something interesting. Is the empty string always in sigma star? Yeah, because all you're tasked with doing is picking 0 things out of the set, or 1 thing out of the set, or 2 things, and putting them all together. Well, is there any way to get something not empty by picking 0 things out of a set? No. So epsilon, the empty string, is always in sigma star. Cool. So then what is a string? So that is an element of sigma star. Yeah, so that's what I'm defining a string to be. It's just some element in sigma star. You can also define it as a finite length sequence of characters, but that's what sigma star is in the first place. Okay. And then one of the most important definitions, but it's pretty simple, a language is a subset of sigma star. And it's so important, I'm going to use a different color. Wow, did you just see that? Nice, nice. Okay. Because this entire class is literally talking about different kinds of languages. So what is a language? It is a subset of all possible strings, essentially. So we are given a specific alphabet to work over. Then we look at all strings of corresponding to that alphabet. Then a language is just a subset of that. So you can think of, for example, the language of English words is just a subset of sigma star, where sigma is all the characters, all the 26 characters. That would be an example. Note here, did I say that the language has to be a finite subset? No, it could be an infinite subset too. Does that say that sigma star itself is a language? Is that true?
No.
Yeah, I never said that it had to be a strict subset. Okay, so one thing that you'll learn over and over in this class, and you probably should learn it early, is that definitions are your best friend in the entire world. So if you're unsure about how something works, appeal to the definition. It'll help you substantially. Okay? Okay. Any questions on these? Okay, I need to get one more definition for your quiz to actually work. For you to be able to do your quiz, I mean. So let's see. Well, we gotta formalize then what it means for a DFA to compute something on an input. So if I looked at our example DFA over here and I asked you, what happens on 0, 1, 0? Then you say, okay, well that goes from Q0 to Q1, then it goes down to Q3, then it goes back over to Q2. So the computation then is what happened along the way. Where did you start and where did you go and where did you end up? So let's see. If I give you that input, 0, 1, 0, how many states are you going to see? So note, the input length has 3 characters, 0, 1, 0. How many states are we going to see, including repetitions possibly? 4, right? Why 4? The start state before we have read any input. So if I have a string of length 1, we'll see 2 states. If I see an input of length 2, we'll see 3 states. If I have an input of n characters, how many states will we see? N plus 1. Okay? Cool. So now we have everything we need. So this is another definition. Let M, so I'm going to define a DFA for you of some kind. So let M, which is Q sigma delta Q0F, be a DFA. So I'm not saying anything about what this machine looks like. I'm just saying it's a DFA of some kind. And let's let W equal W1 up to Wn. So I'll give a meaning to what that, I'll say what that means later. So let's let W be an element of sigma star. So if it's an element of sigma star, what do we call W? It starts with stir and ends with ing. It's a string. What did the W1 through Wn mean? Here, what this means is that each Wi is a single character. So I say that Wi is in sigma. I don't put a star on sigma. I just put just normal sigma, which means that each of the Wi's here is an individual character. Why would we want to do such a thing? Well, in order to execute a transition properly, we need to know each of the characters in the entire string in the first place. Okay? Anyone confused? Okay. So then a computation, so this is the actual definition of M, the DFA, on W, which is the string, is the sequence of n plus 1 states R0 through Rn, where, and then we'll talk more about that later. So a computation, no matter what it is always a sequence of states. That's all it is. I mean, there are conditions, but it's a sequence of states. Okay, well, let's see. Can I just name off any old sequence I want to, or is there a certain order that we have to visit the states in? So like for example, so if we go back to our DFA up here, and I asked you where 0, 1, 0 went, could I just say, oh, the first state's Q2, then Q1, Q0, then Q3? Can I just name them in any order I want? Or is there a certain order you have to take them according to the transitions? It's not a yes/no question, there is an answer.
There is a fix.
There is an order. Okay, good. So let's see. Well, R0, that is the first state in the sequence. That's the very first one. So whenever you turn on a DFA, where do you have to start? What state do you have to start in? Start state, good. So the first condition here is that R0 is equal to the state I've specified as the start state. So R0 through Rn here is just a renaming of states. Because I don't know necessarily what the names of the other states are going to be. I'm just giving a name to them. Okay, well, so the first state has to be the start state. That has to be true. Well, what has to be true of R1, the second state in the sequence? What has to be true of it?
It cannot be the starting state?
It might be. So we could have what is called a self loop, and we can do an example on that. What has to be true of it, though? So let's see. So I'm going to make a little thought bubble over here. So we have Q0 right here. And let's just say without loss of... go ahead.
Oh, I was just going to say, does it have to be a possible destination state?
It has to be a possible destination state, but it also has to have some property, which is that it's the result of taking the transition with the first character. So we're at the start state right now. Well, in order to figure out where to go next, what is the character I have to look at in the string itself, W? W1 is the first character because we haven't executed a transition yet. Yeah, so we got to look at whatever the transition is labeled W1, and then that's going to lead us to some other state. Maybe the same state, but it leads us to a state. Okay, great. So that tells us that that R1 is the result of what? Well, how did we figure out what the next state in the line is? Well, we had to look at what the start state was and what the first character is, and then look at the machine and figure out where to go. Well, how do I figure out where to go based off what the machine says? Yeah, the transition function. The transition function says, let's go back up. The transition function says, what is the origin state, what is the input character, and where are you going? So it'll output where you're going. So R1 then is equal to delta of Q0, not Q0, my bad. Should be R0 and W1. So we go from the state R0, we read the character W1, and we end up in the next state along in the chain. How do you think we can get to R2?
It's just delta of R1 W2.
Yes, good. So R2 is delta of R1, the previous state, with the next character in the line. Exactly. Someone else, how do you think we get to R3?
Probably this would be R3 is equal to delta of R2 and W. Oh, sorry, R2 and W1, W3.
Yes, exactly. So how do you think we can get to then R of I plus 1 in the general case? Yeah.
R of I and then W of I plus 1.
Exactly. But does this have to be true for every single I value? Or just some? Does it have to be true for every state in the sequence or just several of them? It has to be for all of them. So this has to be true for all, let's see, for all I at least 0 and strictly less than n. The bounds on I here are just so I don't go outside the bounds of the state numbers. Okay, cool. So that tells us we have to start in a start state and we have to do exactly what the transition function says to do all along the way. Any questions on that? We'll do an example. Okay, so let's do an example. So let's make this DFA. So I always make up DFAs on the fly, so if this ends up not being a good DFA, well, I need to be better at this then. So Q1, okay, so this is just a random DFA that I made. So it's got 3 states in it. So let's formally specify what this machine is. So how many pieces do we have to define in order to formally define DFA? 5 of them, right. So what's the first one? Q, exactly. So Q is what?
Q0, Q1.
Exactly. It's always a set. Always remember it's a set. Q0, Q1, Q2. Super. Well, what's the next thing that we should define? The sigma, the input alphabet, exactly. So what's the input alphabet in this case?
0.
It's 0 and 1. Yep. So that's pretty easy. Always leave the transition function last. Pro tip. Leave the transition function last because that's the hardest one. And I'll show you an easy way of doing it formally. So what's the next one after the transition function?
Q0.
Q0. So what's the start state in this case?
Q0.
Q0. So this notation looks a little weird, Q0 equals Q0, but that's just saying the start state is named Q0. Could I have equally named it Q2? Yeah, I could have equally done that. What about the final states? F.
Just Q1.
Just Q1. Is it a state name or is it a set of states? Okay, so always remember that F is a set of states. But in this case, it just happens to have one thing in it. Okay, any questions on those four? Oh, so we're completely done defining this DFA, right? So we got to do that transition function business, right? So there are two camps that you could subscribe to. I'm going to show you the easier one, but I'll also show you the harder one, or at least more time-consuming one. So this is the easier one. So instead of talking about the transition function, we're going to make a transition table, which will convey the same information. So here's how the transition table works. So we're going to make a itty-bitty table like this. So the rows are going to correspond to the origin states, which could be Q0, Q1, and Q2. Actually, it's just a list of the states, nothing special there. And then the columns are going to be each of the input characters, which is 0 and 1 in this case. Actually, I'm going to move it a little bit. Move it there. Okay, so how do you fill this table out then? What you're going to do is the entry corresponding to some row or column is the result of taking the transition function with that state and symbol. So for example, in the first row we have Q0, and in the first column we have 0, the input character 0. So in the diagram, where does Q0 go on input 0?
Q0.
Back to itself, right. Oh, by the way, I should label this too. The arrows that go from a state to itself, we call those self loops. I mean, it should be pretty clear what that means, but yeah.
Can you have multiple possible states going on? So like the one going from Q1 to Q0 is fine, along with the Q1 going to Q2.
Oh, that was my mistake. I shouldn't do that. Yep. Thank you. Yeah, thanks. Yeah, I think it's now correct. Yeah. What you were saying is right, because you can't, in a DFA, have two transitions out on the same symbol. You're right. Good. We will talk about a machine that can, but not now. Okay, so Q0 on input 1, where does it go? It goes to Q1. Q1 on 0, where does it go? Back to itself. Q1 on input 1, where does it go? Q2. And what about Q2 on 0 or 1? It goes back to Q1. So the comma here on this transition, you may not be sure what that means. This means multiple transitions. So instead of having two separate arrows, one being 0, one being 1, we're just having them smushed together on one transition. You can either take 0 or you can take 1. Okay, well, remember the term total function I was talking about earlier, where every state and input symbol pair had to be defined. In terms of the table, that means that there are no gaps in the table. So if you're making a DFA and you're making the table like this and you have something that is not filled in, that means it's not a DFA. That's all that means. Okay, any questions on that? So I think this is the easier way. The harder way, or more intensive way, is to say delta of Q0, 0 equals Q0, delta of Q0 on 1 equals Q1, delta of Q1 on 0 equals Q1, and I'm already bored. So you could do this method or this other method. Either one's fine. It's just that I think the table's easier. Any questions on how we specified this DFA? Yeah.
So this table, like, is that what delta represents?
Yeah, so it's a formal specification of what delta is, yeah. So instead of having a picture drawn for you, a table is a formal way of doing it. And we can provide a table pretty easily in a computer. So, other questions? Okay, one more definition, I promise, and we're almost done anyway. So this is probably even more important than language. So a language, oh no, never mind. We're not there yet. So we're going to talk about the language that is accepted by a machine. So we were talking about that machine with 4 states, and we said in English, oh, it's just all the binary strings of odd length. So we need to define that formally too. So, oh wow, I'm forgetting other definitions. Okay, oops, my bad. So an accepting computation so the computation we just talked about, where you just talked about those n+1 states, does that tell you anything about whether the machine accepts the string, ends up in a final state? Or it just tells you the set of states that you visit along the way? Does it tell you whether you accept the string? No, and you can tell by looking up at the definition. It just says what the next state is in the line. It doesn't say whether it accepts or not. So an accepting computation is simply one where the last state in the chain, R sub n, is a final state. Okay? And then the language accepted by a DFA called M is the set of all strings where M has an accepting computation on it. So it's just all the strings where M says, yes, we accept the string. So like for the 4-state one, it's just the set of all, it would be all binary strings that are of odd length, but it's just the set of all binary strings of odd length in this case. Okay, any questions on that? We'll talk about the really important definition on Monday. So I'll see you then.